So far, we've been talking about sound, how it's created. Now we're going to get into the fact that how sound propagates. And in the last section, we're going to talk about how we hear. So the next two chapters are going to be how the sound gets to us. So we are going to do sound propagation. So my first question for you is, how do you get something from point A to point B? The answer is you pick it up and you take it with you. However, how do you get energy from one place to another? So energy doesn't come in a bundle. And so we can't just pick it up and move it. We have to have some other mechanism of moving the energy. So one way that we can transfer energy is we can transfer it with matter. So for example, if you wanted to break a glass, what would you do? You would hit it with a rock. If you throw a rock at it, it carries the energy that it gets from your hand, it hits, and it breaks. But that means you transfer actual matter. On the other hand, you can also transfer energy by transferring it with a wave. So a wave is a transfer of energy without the transfer of matter. Yes?
Context of like sound, the there are waves, but even though it's still like hitting with all like the air molecules back and forth, so that doesn't count as transferring.
So when I'm speaking, do you feel the air molecules coming towards you? Right. So the medium moves as the wave passes by, but then it comes back to its original shape. So I'm making the noise, right? It's being transferred in the medium, and then your ear is responding to the pressure that my noise created that was transferred into the medium that transferred into your ear. But you don't feel any molecules coming towards you, right? So for example, let's take the example of a rock hitting the window. The fact that the rock traveled and actually impacted is the transfer of matter. But in a wave, there is no transfer of matter.
So even though it passes through matter,
there's no transfer of matter. So if you would feel the molecules hitting your face, that would be wind. Right? That's a transfer of matter. But in the sound, there's no transfer of matter. So the matter stays where it is. Yes, it goes away from its equilibrium place a little bit, but it doesn't transfer with the sound. That's a great question. Does that make sense?
Yeah.
Is that clear to everybody? So what is a wave? A wave is something you create. So take an example of this girl. She's holding on to a string, correct? The string is the material that she has. If she shakes it up and down, a wave will start. She stops, the wave continues forward down the string. So there is no matter that transferred. Only the energy that she's putting into the system gets transferred. Good? The number of times she moves her hand up and down creates the frequency of the wave, how often a wave happens. It also creates an amplitude, that is the height of the disturbance. And in terms of sound, think of amplitude as the volume control. Larger volume means larger amplitude. Smaller volume means smaller amplitude. Frequency is how often she moves her hand up and down. So physicists generally look at the world two ways. One, they look at it, which is called a particle model, and two is what is called a wave model. So in a particle model, you are only concerned with the big picture. So for example, if this girl is drinking coffee while she's driving a bicycle, you don't care. She is a box. Do you remember drawing this box? It had a normal force, it had a weight that was mg, it had an acceleration that was this way, right? That is called a particle model. This box could be your car, it would be your 18-wheeler, it would be your airplane. No matter what you have as a system, it will just be called a particle. Whereas in the wave model, everything is treated as a wave. So for example, the waves around you, listen for them. There's sound all the time around you. There's also light all around you. There's also cell phones, right? You have your cell phones, your radio signals, your TVs, your computer signals, everything is a wave. It will be extremely difficult to find a spot on planet Earth where you are completely waveless. There will be no place that you won't have some kind of a wave, whether even underwater, right? You will have light or you would have water waves. Yeah, so it will be very hard for you to find a completely waveless spot on planet Earth. If nothing else, there will always be some sound or light. There is no such thing as complete darkness, right? There's always light. Okay. And because everything that we experience in the world is a wave, at least 2 of our senses are wave detectors. I would even hazard a guess that 3 of our senses are wave detectors. So what are our 5 senses? Sight, smell, hearing, touch, taste. So eyes are detectors of light waves. Ears are detectors of sound waves. And touch detects waves that are created. But definitely 2 out of the 5 are definitely wave detectors. So if waves are so important, let's look for some properties of them. Number 1, waves transport energy and information from one place to another. Some waves need a medium to do this, but very important, the medium itself never gets mostly never gets transferred with the wave itself, except for the ocean waves, right? Ocean waves actually travel with the wave. So the medium, if you notice here in this picture, the medium just goes back and forth as a wave. So buoys on water, yeah? As the wave passes by, what do? They just move up and down. So a wave passes and the medium itself just goes up and down, right? Okay, so then there must be many, many different kinds of waves. And the answer is absolutely. There are many, many different kinds of waves. For example, light waves, the disturbance that causes the wave is a change in electric and magnetic field. In sound wave, the disturbance is pressure and density. These 2 things are important, but pressure is the one that's kind of more important for us. Density is important, and we'll see it later. And density is defined as mass per unit volume of any substance. But important to remember, it's written in red, the medium reverts back to its undisturbed state after the disturbance has passed by.